Hey everyone, welcome back. In this video, we're finally going to start solving some exponential equations, right? We introduced this idea of a logarithm as a tool to help us solve these exponential equations, and we also started talking about all these logarithmic properties that are going to help us complete this task of solving an exponential equation. So let's go ahead and get started. In this example, we're asked to solve the exponential equation 5 to the power of x is equal to 100 using log base 5, the common log or log base 10, and the natural log or log base e. So remember, in order to solve any equation, we're really trying to isolate a variable and get that variable equal to a single number. So in our case here, we're trying to solve for x, and we can actually accomplish solving for x using log base 5 really quickly just by rewriting our equation from its exponential form to its logarithmic form. And so remember, if we start with the exponential form, 5 to the x is equal to 100, the corresponding and equivalent logarithmic form of that equation is going to be log base 5 of 100 is equal to x. Remember, what comes out of our logarithm is the exponent that we have to raise our base to get what is inside of our logarithm, or what is the output of our original exponential equation. That's great. That didn't take very long at all. We have our solution for x. X is equal to exactly log base 5 of 100. But now the question is, what is log base 5 of 100? What is that number equal to approximately? Is it like 5, 6, 2, 3? We can kind of figure out like 5 to the power of 2 is 25. 5 to the power of 3 is 125. So it's got to be somewhere between 2 and 3. But we can't just plug in log base 5 of 100 into most calculators. Most calculators are only programmed with log base 10 and log base e, the common log and the natural log. So we're going to need to figure out another way to solve this equation if we want to use our calculators to approximate an answer. So our first time around solving for x using log base 5, we didn't have to use any of our fancy logarithmic properties that we've developed. All we had to do was change the exponential equation to its logarithmic form. Now for these other bases, log base 10 and the natural log, we are going to have to involve some of these logarithmic properties. All right, so now we're going to go ahead and solve our exponential equation again, but this time using log base 10 or the common log. And so here we have our exponential equal to a constant number. That's a great place to be in if we want to use a logarithm to help us solve an exponential equation. Our next step in this kind of general procedure that we'll outline later is taking the log of each side of your equation. And so here we want to work with log base 10 or the common log. So we're just taking log base 10 of each side of our equation. And so now we have an equivalent equation that we've taken the logarithm of both sides of, and now we can start using some of our logarithmic properties. In particular, we're going to want to use our power property for logarithms. What our power property for logarithms says or allows us to do is take an exponent from inside of our logarithm and bring it out front as a factor. Well, what is the exponent inside of our logarithm on the left-hand side? It is our variable x. X is now going to be brought out front as a factor, and so we can rewrite our left-hand side as x times the natural log of 5, and that's still going to be equal to the common log of 100. I think I misspoke there and said that was the natural log of 5. That's just because I use the natural log so often. All right, so now we've solved this equation a second time around, and we saw that x was equal to the common log of 100 divided by the common log of 5, and we can actually simplify that to 2 over the common log of 5 if we wanted to, just because we can evaluate the common log of 100 pretty easily. But I actually want to leave this in this form for a particular reason. We'll see that reason after we talk about our last approach, solving this exponential equation using the natural log instead. And so, well, the steps for solving our exponential equation using the natural log are going to be exactly the same and mimicking the steps we just used when approaching it with the common log or log base 10. So our first step is to take the log of each side of our equation. Now we're taking the natural log of each side, and then we use the power property of logarithms to take our variable, our exponent of x, out front. And so we're using that again on the left-hand side here. Our left-hand side becomes x times this number, which is given by the natural log of 5. That's equal to the natural log of 100. And now we can solve for x just by dividing that factor of the natural log of 5 away. And what we end up with is the natural log of 100 over the natural log of 5. And so we solved this equation in 3 different ways, and all 3 of these answers are exactly the same. They're all equal to x, the number we're looking for here. And so that actually tells us another interesting thing here. That's that log base 5 of 100 is exactly the same as log base 10 of 100 divided by log base 10 of 5. And that's exactly the same as the natural log of 100 divided by the natural log of 5. And so we can start noticing some similarities and resemblances here between our answers. And we can kind of notice, well, for these last 2, our procedure is going to be the same no matter what base we use for our logarithm. And so we'd always be taking the logarithm of the constant and dividing that by the logarithm of the original base of our exponential. And through this observation, we can actually discover or write down and kind of prove a 4th important logarithmic property, what we call the change of base property or the change of base formula. And so what our change of base property for logarithms allows us to do is take the logarithm of any base starting with, say, b, and rewrite that in terms of log of any other base a, where a still has to follow all those conditions of a base where it has to be positive and not equal to 1. So if we start with log base b of m, we can always rewrite that as log base a is our new base, log base a of our original input m, divided by log base a of b, log of our old base. So log of the new base of our original input divided by log of our old base is how we use our change of base property. So nowadays, the main application of our change of base property is just to allow us to rewrite our logarithmic expression using a more familiar or useful logarithm like the common log or the natural log, a log that is programmed into most calculators.